Hello, welcome back to Learn from a Layman. I'm Carl Christensen. I'm back with Tim and with Matt, and we today will be discussing trigonometry, some other mathematical functions and equations if we get time, but we're going to start with trigonometry today, which is not exactly something that I'm once again strong in, and as if you've listened to these podcasts in the past, Matt generally takes us through the math of the mathematical subjects. So Matt's going to be our guide in this one as well. We asked him to handle this, but he started rambling and we lost interest. So
I think you're just jealous of my grasp of very obscure and abstract concepts that don't make any sense.
Yeah, like half of 33.
We will not speak of this.
Okay. All right. Anyway, let's go ahead and let Matt walk us through some trigonometry. Matt?
Okay, so trigonometry, you may be wondering, what is trigonometry and why do I care? And that's a very good question. For most of you, you care because you're in a trigonometry math class and you better pass, or either your parents are going to be mad, or you're going to lose your scholarship, or some combination of those things. If you're not wondering, why do I care about trigonometry, that means that you already understand it, and there's nothing we can teach you further. But
you just limited our audience to like some college or high school students.
Well, specifically high school and college students that are in trouble
okay.
because they don't understand trigonometry. So
great.
Yeah, I know. I'm moving on.
Yes.
Okay. Trigonometry, from the Greek trigonon, I'm reading straight from Wikipedia, meaning triangle, and metron, meaning measure. Okay, it's the study and science and math of triangles, how to solve a triangle and understand them, and so on and so forth. And when we talk about solving a triangle, we're going way back to the basics here. A triangle has 3 sides. Because of that, it also has 3 angles between the sides, thus the name triangle. Well, silly that we're saying that, but we are.
Well, let's check. Tim, are we following?
You lost me at 3, but it's all right. Keep going.
That's okay. So the thing is, yeah, we all know what a triangle is, but it turns out that in many cases in mathematics, science, engineering, astronomy, physics, the obstacle course that you need to solve using a 2x4, trigonometry can either be required or make your life significantly easier. And I throw out that last one because, yes, that happened. I used the Pythagorean Theorem to solve an obstacle course and avoided having my team metaphorically swept down a river and penalized 10 minutes. But
are you going to explain the Pythagorean Theorem as well?
Yes. We're going to hit all of this stuff. So when we talk about trigonometry, we're talking about solving triangles. And what I mean by solving triangles is finding the values of the sides or the angles or both. You find triangles all the time in your trigonometry textbook, but you also find them all the time in nature, in engineering, in the lab, in a number of applications. It turns out that those story problems that you love in your textbook are actually the only ones that matter because they help you see the triangles in real life, and then when you encounter them, you know how to deal with them and solve them. So let's talk about what our objectives are. I kind of mentioned it. The objective of trigonometry is to help a person solve a triangle, to find the value of an unknown side, assuming that you have the values of the other sides or angles, or find the value of an unknown angle. If you, as long as you have parts of the triangle, trigonometry is the science of figuring out the other parts. And we use 6 basic trigonometric functions to do that. These are the sine, the cosine, the tangent, the secant, the cosecant, the cotangent. And if you didn't memorize those as I said them, that's okay. We'll go through them one by one and what they are and what they mean. So, Carl, let's say you have a triangle, as you often encounter in your daily life, and you know the length of 2 of the sides and the angle between the sides. Can you imagine that?
I can imagine that.
Yeah, imagine holding chopsticks in your hand, and the angle that the chopsticks make as they extend past your hand. You have the 2 sides and you have a specific angle. If you wanted to put another line connecting the ends of those 2 chopsticks, how long would that line need to be, and what angles would that line make with the 2 chopsticks that you have? Well, you can figure that out if you know what to do and how to use the trigonometric functions. The sine, the cosine, the tangent, the secant, the cosecant, and the cotangent are the things that you use to solve that. Let's stop right now and really quickly talk about right triangles.
Sorry, maybe we should discuss because I thought you were actually going to ask me to solve some numbers here, and I was going to fail miserably. But yes,
no,
please.
Anytime you're given a problem involving chopsticks, the answer is use a fork. But, moving on back to triangles.
Yeah. I think you just offended our East Asian listening.
America.
Not even going there. Anyway, let's talk about right triangles specifically. A right triangle is a specific type of triangle where one of the angles equals 90 degrees. Quick question. What is the total amount of degrees in the angles of a triangle? If you take the 3 angles and add them together, what number should you get?
Ooh, 180.
Very good.
Wait, $1, Bob.
No, not dollars at all. Every triangle in the world, when you add all of the angles together, it comes to 180 degrees. A right triangle is a specific type of triangle where one of those 3 angles is 90 degrees. The other 2 angles, when you add them together, add to 90 degrees, and so you get 90 plus whatever equals 180. But right triangles are kind of the easy ones to use trigonometry on to solve for a missing side. And we'll use a right triangle to talk about the first 3 trigonometric functions, the sine, the cosine, and the tangent. What these are ratios. The sine, the cosine, and the tangent are ratios of one side of the triangle with another side of the triangle. The sine and the cosine are, and specifically when you have a right triangle, obviously you have 3 sides, but the longest of the 3 sides is called the hypotenuse. That's a fun word to say fast if you're the type of person that derives enjoyment from saying words fast. But the hypotenuse is the side that is opposite to the 90-degree angle. It is the side that the 90-degree angle does not connect to. So those 2 other sides that are not the hypotenuse, those are the 2 that come into play when we talk about the sine and the cosine, because the sine and the cosine are the ratios of one of those 2 smaller sides to the hypotenuse. And so we'll start with the sine. If I have a triangle and a right triangle, and I know right off the bat one of my angles, right?
Right, 90 degrees.
Yes, because it's a right triangle. Let's say that I know one of the other angles, only one. And let's say that I know the length of the hypotenuse. So I have one side, I have the hypotenuse, and I have the right triangle, and I have one of the other two angles. That's fine. Let's say that that other angle is 60 degrees. Now, if I know I have a right triangle, and I know one of the other angles, my 60-degree angle, do I know automatically what the third angle is?
You do.
Yeah, I totally do. It's whatever I need to add to 60 to make 90 happens to be 30. So if I had a 90-degree angle for my right triangle, and then my second angle was 35 degrees, I would expect that the other angle would be 55 degrees. So going back to our right triangle, imagine, if you will, you have your 90-degree angle. Say it's at the bottom left. Imagine you have the 60-degree angle. Say that that is at the bottom right. And imagine you have your 30-degree angle. It is at the upper left. Now, I know the hypotenuse. It goes from my 30-degree angle to my 60-degree angle. And let's say that it is 1, because that's a fun number. Now, what if I want to...
It's the loneliest number.
Okay,
I'm sorry. Go ahead.
It's... we're in different time zones. I'm not able to adapt as quickly as Carl is here. All right, that's fine. So let's say I want to solve for the other two sides of that triangle. Well, because I know the length of my hypotenuse, I know that it's 1. Because I know my other angles, 30 degrees and 60 degrees, and because I know what a sine is, because I listened to this podcast, I can figure that out. Okay, well, let's solve first for the length of the side that does not touch the 60-degree angle. It's the side that goes from my 90-degree angle to my 30-degree angle. To do that, I'm going to use the sine function, or the sine is of an angle is a ratio. And every angle in the world has a known sine and a known cosine and a known tangent and all of these things. These values are known. And if I know the angle, I know the ratio of those sides, and I can use that to very quickly solve for my unknown side. So let's go back to this. The sine of any given angle is the ratio of the opposite over the hypotenuse. I mentioned I know my hypotenuse. My hypotenuse is 1, because that's easy. The sine of my 60-degree angle then will tell me the number that if I divide that number by 1, I will get the length of that other side. Okay, what does that mean? Sine of 60 degrees. Sine of 60 degrees, the actual value is 0.866. What that means is that the opposite side, my unknown side, if I divide that number by 1, I should get 0.866. Well, now I have a simple algebra equation that I can solve, and I made it really easy because I said my hypotenuse was 1. 0.866 equals x divided by 1. X, therefore, must be 0.866. The opposite side from that 60-degree angle is a length of 0.866. And I just figured that out. Now, the ratio holds true no matter what the length of my hypotenuse is. What if my hypotenuse was 10? Well, then my equation would be that the opposite over the hypotenuse still equals 0.866. So I have some number, the opposite of some length. That number over 10 equals 0.866. Well, solving that very simple algebraic equation, I get that my unknown number is simply 10 times 0.866. It's 8.66. And I can very quickly solve for my unknown side using that sine ratio. Well, that's neat. I figured out the length of the opposite side. Now, what if I want to solve for the length of the side that does touch my 60-degree angle? The one that is not the hypotenuse, but the one that connects my 60-degree angle to my 90-degree angle. That side is called the adjacent. Adjacent because it touches the angle in question. My opposite side does not touch the 60-degree angle. The adjacent side does. Well, to solve for the adjacent, I use a different ratio. I use the sine. The sine is defined as the ratio of the adjacent over the hypotenuse. Okay, so what's the cosine of 60 degrees? And it turns out it's 1/2. I do the same algebraic equation. My unknown length divided by my hypotenuse equals 1/2. Doing some quick algebra, I learned that my unknown length equals 1/2 times the hypotenuse. If my hypotenuse is of length 1, then my adjacent side will be 1/2. If my hypotenuse is 10, then my adjacent will be half of that. It will be 5. And using those two ratios, I can very quickly solve for the unknown sides of my right triangle, which is neat. I can do all these things as long as I know the hypotenuse. What if I don't know the hypotenuse? Then what do I do, Tim?
That seems
You
about right
call
for Tim.
an expert.
You call an expert, yes, or you listen to this podcast.
That's right.
Well, I know my angles, and let's say that I know the other two sides, but I don't know my hypotenuse. In fact, I don't even need to know both of my other two sides. Let's say I just know.
Don't you just
one.
need to know one side and two
Yep.
angles?
Yeah. Well, and in a right triangle, it's pretty easy. If you know
Right.
two angles, you know three angles.
Yeah, right.
Because right triangle. But yeah, all I need is to know one of the sides in a right triangle. If it's not the hypotenuse, though, can I use the sine or the cosine? Well, not yet. First, I have to figure out what the hypotenuse is, and to do that, I have to figure out what the other two sides are. And this is where the third trigonometric function comes into play, the tangent. The tangent is defined as the ratio of the length of the opposite side over the adjacent side. So let's go back to my 30, 60, 90 degree triangle, and specifically, let's go back to my 60-degree angle. Let's say I don't know the hypotenuse, but I do know the length of the, which one do you want? The opposite side or the adjacent side, Carl?
Adjacent.
I know the length of the adjacent side. I also know that I have a 60-degree angle, and because I know that, I can use the tangent function. The tangent of 60 degrees is 1.732. I didn't make this up. That's just what it is. And using that, I know that the opposite side over my adjacent, which Carl told me I know. What's the length of my adjacent, Carl?
10.
10. It's 10. Okay. I know that the opposite side over 10 equals 1.732. 05081. Well, anyway, that's fine. Again, doing a very quick algebraic equation. My unknown over 10 equals 1.732. That means my unknown equals 10 times 1.732. My unknown equals 17.32. And I just figured out the length of that unknown opposite side. Now, at this point, I know two sides of the triangle, don't I?
Yes.
Yes. Can I very quickly figure out the length of the other side?
You can.
Yeah, I can. And I can do it by going back to a sine or a cosine function. And in fact,
It's
once
probably
I had
also a
the
good
opposite
time
of the
to.
adjacent, I could have used the sine or the cosine function either earlier. But anyway, sorry. Go ahead, Carl.
I was going to say this might be a good time. I don't know if you do this later, but to kind of give it a real world example where this might be useful beyond a trigonometry class or what some other geometric class or engineering class you might be in. in the real world, let's say you want to know the height of a building or the height of a specific lamp post or something which you can't like just climb up and measure. This is where you could use something like this, right? You can essentially create a right triangle in a 90-degree angle from the base, walk out a certain specific distance so that you then know one side of the triangle, and then you just if you can get the angle from where you're at to the top of the object that you're trying to measure, then you've got your triangle set up and you can solve.
Yeah, the classic example is find the height of a flagpole using its shadow.
Right.
Well, assuming the ground is flat, the shadow and the flagpole will form a 90-degree angle, so you have a 90-degree triangle. If you walk to the tip of the shadow and you use a protractor or compass or something to measure the angle between the tip of the shadow and the tip of the flagpole up in the air, you've now figured out a second angle. You've got your 90-degree angle at the base of the flagpole, and you've got whatever it is that you measured, say it's 60 degrees from the tip of the shadow to the tip of the flagpole. You can measure the length of the shadow, and then using the trigonometric functions, you can figure out how tall the flagpole is. So in the case of that flagpole shadow example, if I'm standing at the tip of the shadow and I'm at that angle point looking at the top of the flagpole, the shadow is going to be my opposite or my adjacent?
The shadow's going to be adjacent.
Yes, because it's connected to me.
Yes.
The flagpole itself is going to be the opposite because it's not touching me at all. And an invisible line running from the tip of the shadow to the tip of the flagpole would be the hypotenuse. Now, the easiest way to solve for the height of the flagpole would be to use the tangent function. If I'm there and I'm measuring a 60-degree angle between the tip of the shadow and the tip of the flagpole, then I know that the length of the flagpole, the opposite, divided by the length of my shadow, the adjacent, is equal to the tangent of 60 degrees, which happens to be 1.73. How long was my shadow, Carl? 5 feet, 10 feet, 150 feet?
10 feet?
It was 10 feet, let's say.
Yes.
So I measured my shadow to be 10 feet. I know that the opposite divided by 10 has to equal 1.732. Doing some algebra, the opposite, the length of the flagpole, equals 1.732 times 10. Therefore, the length of the flagpole is 17.32. If I measured a 60-degree angle. If I measured a 30-degree angle, well, what's the tangent of 30 degrees? It's a different number. It's 0.557. If I'm still measuring a 10-foot shadow, that means that my flagpole is 5.7 feet tall. That's a pretty lame flagpole. But anyway, that's a quick way that you can measure that you might find a practical use for a trigonometric ratio in your day-to-day life as a city flagpole measurer. Let's talk about another property of right triangles, and this is a little bit more geometry than trigonometry, but it's still important. Have you heard of the Pythagorean Theorem? Well, if you're listening to this podcast, we will assume no. But the Pythagorean Theorem is a way to determine any of the lengths of a right triangle, assuming that you know the other two lengths of the right triangle, and you don't even need to know the angles at all. That can be a complete mystery to you. But the Pythagorean theorem basically states that the two non-hypotenuse sides, the opposite and the adjacent from whatever point, basically whichever sides are not the hypotenuse, if you take those two sides, call them A and B. If you square A, you take A times A, and you take side B and you square that, b times b, and you add the two together, so a squared plus b squared, well, it turns out that that is equal to the hypotenuse squared. Call the hypotenuse c, and your Pythagorean theorem reads out as a squared plus b squared equals c squared. So let's say that I have a, let's go back to our little flagpole example. For some reason, I know the height of my flagpole. I've measured it and it's 10 feet tall. I've also measured the length of the shadow, and it's 5 feet tall, or 5 feet long, rather. Apologies. For some reason, I am now obsessed with knowing the length between the tip of the flagpole and the tip of its shadow, that length being the hypotenuse. That would be c squared. I'm sorry, that would be c, not c squared. Well, because I know the Pythagorean theorem, I can now figure out what the length is between the tip of the shadow and the tip of the flagpole. My flagpole is 10 feet tall. That's A. I'm going to square that. 10 times 10 is 100. The length of the shadow is B. That's 5 feet. I'm going to square that. 5 times 5, that's 25. I'm now going to add the two together. So I get 100 plus 25, and I have 125. That number is equal to the length between the tip of the flagpole and the tip of its shadow squared. And so if I take the square root of that number, then I can get the length, that length, the length between the tip of the flagpole and the tip of its shadow. So I take the square root of 125, and it's kind of a messy number. It's 11.18. But that way I can very quickly figure out what the hypotenuse of any given right triangle is. Now this works if I don't know one of the other sides, but I do know the hypotenuse. If I know the hypotenuse, I know what C is, and I know one of the other sides, well then doing some algebra, I can very quickly solve for that missing quantity. But that's kind of a property of triangles, of right triangles specifically. If I don't have a right triangle, then I have to do some other fun stuff that we'll get to in a minute when we talk about the law of sines and the law of cosines. But let's talk about the three remaining trigonometric functions. We talked about the sine, the cosine, and the tangent. Those are the first three. Again, the sine is the ratio of the opposite side divided by the hypotenuse. The cosine is the adjacent divided by the hypotenuse. And the tangent is the opposite divided by the adjacent. Okay, so the other three trigonometric functions relate to the first three that we talked about, the sine, the cosine, and the tangent. The other three trigonometric functions are in order: the cosecant, the secant, and the cotangent. The cosecant is, well, and the secant and the cotangent are respectively the inverses of the sine, the cosine, and the tangent. What does that mean? Well, if the sine of an angle is the opposite over the hypotenuse, the cosecant is the inverse of that. It's the hypotenuse over the opposite. It's a way to make the math a little bit easier if you know, depending on which side you know. If you know the hypotenuse or you know the opposite, it's a little bit algebraically easier to use the sine or the cosecant, depending on which one you know. Okay, great. The others are the same way. The cosine is the adjacent over the hypotenuse. The secant is the inverse of the cosine. It's the hypotenuse over the adjacent. The tangent is the opposite over the adjacent. The cotangent is the adjacent over the opposite. They're connected trigonometric functions, and you can use them to solve virtually any triangle in existence if you use them appropriately. Now, let's say though, I said any triangle in existence, and all I've talked about is right triangles. Well, what if I don't have a right triangle? What if I have a messy, gross triangle that doesn't have a 90-degree angle anywhere inside it? Then what?
Give up.
No, you turn into this podcast so you can figure out what to do.
Right, that's why I'm here.
Yes. Using these ratios, though, which hold true for any triangle out there, you can still find your unknown values, your unknown angles, and your unknown sides. And if you don't have a right triangle, well, then you might end up having to use something called the law of sines or the law of cosines. The law of sines is actually pretty simple. For any triangle in existence, the three trigonometric ratios the sines of the three angles in that triangle and the ratios that those sines represent, they're all going to be related. Now, what if I have a triangle and I've named the angles A, B, and C, as I do? The law of sines says that the length of the side that is opposite my angle divided by the sine of that angle is equal to the length of some other side divided by the sine of the angle that is opposite to that side. Okay, that's very hard to give someone a clear picture of verbally, but I'm going to try anyway. Imagine my flagpole example. All right, now that's a right triangle, so imagine that the flagpole just survived an earthquake or a hurricane and is now tilted over a little bit. So it's not making a 90-degree angle with the ground. It's still sticking up in the air, but it's at some skewed, slanted angle. It's casting a shadow, and that's going to be on the ground, and there's going to be some length, say a piece of rope that you've tied to the top of that flagpole, and you've driven it into a stake into the ground at the tip of its shadow. You now have a triangle. There's not a 90-degree angle anywhere on it, but it's there. Now, we're going to say that the angle at the top of that flagpole is angle A. What side is going to be opposite to A? Well, it's going to be the shadow that's on the ground. That shadow does not touch angle A. Now, let's say that the angle where the flagpole sticks into the ground is angle B. Well, what side is going to be opposite B? It's not going to be the flagpole itself, and it's not going to be the shadow. Those both touch B. The opposite is going to be that string that you ran from the top of the flagpole to the end of the shadow. That's going to be side B, opposite angle B. And then finally, angle C is going to be the angle where you've plunked that string into the ground at the tip of the shadow. And side C, opposite angle C, is going to be the flagpole itself. Okay, going back to the law of sines. The length of the shadow is A, and the angle at the top of that flagpole between the flagpole and the string is angle A. The law of sines says that the length of the shadow divided by the sine of angle A is some number. I don't know what it is, but it's some number. Now that number will be the exact same as side B divided by angle, or divided by the sine of angle B. Side B was that string, and angle B was that skewed angle between the flagpole and the ground. If I take the length of that string and I divide it by the sine of B, I will get the same number as if I had taken side A, the shadow, and divided it by the sine of angle A at the top of the flagpole. Likewise, if I take the length of the flagpole itself, C, and divide it by the sine of angle C, the angle between the shadow tip and the tip of the flagpole, I will get that exact same number. And so this gives me a powerful algebraic equivalency, where if I know 3 of those things, I can solve for the 4th one. If I know 2 angles and a side, then I can solve for the unknown side. If I know 2 sides and an angle, I can solve for an unknown angle. Does that make sense?
I think so. Yes.
Yeah. Again, this is much easier to draw, and you know, I'd encourage you to basically every time you listen to one of our podcasts, sit down in front of a whiteboard and start scribbling, and then send pictures of what you've scribbled to Carl, and we'll post it on his website. Never mind.
And that will become our new logo.
Yeah, indeed. But that's the law of sines. That allows you to solve unknown sides and unknown angles. And that law is universally true for all triangles, not just right triangles. The law of cosines is a little bit more complex, and I don't want to go into it because it's even harder to verbalize without drawing it out. But I will. I'll state it anyway. It's another algebraic equation that tells you how things relate to each other. And if you know parts of this equation, then you can solve for an unknown part. The law of cosines basically says that the length of side C squared, that's going to be whatever's opposite to angle C, the length of C squared equals length A squared plus length B squared minus 2 times length A times length B times the cosine of the angle at C. I'm not going to try to illustrate that one, but if you have questions on it, look it up, and you don't have to memorize it. The internet was built so that we didn't have to memorize these things. But using this equation, if I have angle C and I have length side A and B, I can now solve for the side at C. That cosine law applies to all of the sides and all of the angles. It's not just C squared equals A squared plus B squared minus 2AB cosine C. It's also A squared equals B squared plus C squared plus blah, blah, and B squared equals A squared plus C squared minus 2AC cosine B. It works for all of the sides and all of the angles. So if I know 2 of my sides and I know 1 of my angles, the other angle, then I can use the law of cosines to figure that out. Now, when would I use the law of cosines versus the law of sines? I didn't really explain that, and I should. Basically, you use the law of cosines when you know 2 of the sides and you know the angle that is between the 2 sides. That's basically, you would know side A and B and angle C. The law of cosines doesn't help me if I know A and B and angle A or angle B. The law of cosines only works if I know A and B and angle C, or if I know A and C and angle B. Basically, I have to know the angle that is between my 2 sides. Now, if I don't have that situation, then I can use the law of sines. The law of sines is the one I use when I know either 2 angles plus 1 of their opposite sides, or I know 2 sides plus 1 of their opposite angles. If I know angle A and side A, and I know side B, then I can use the law of sines to find angle B. If I know angle A and side A, and I know angle B, then I can find side B. And then I use the law of sines for that. However, if I'm in a case where I know side A and B and angle C, then I have to use the law of cosines. You select the law that you use based on the information that you know and the information that you don't know. Again, much easier to understand visually, but I hope that we're able to give you some kind of understanding of this one. There's a quick Google search of the law of cosines illustrated. The images will kind of graphically show you what you have available in terms of how to find an unknown based on what you do know.
The important thing here is, like I said, so you just went over the laws and the numbers you're solving for, the angles you need to know, and so the math part of it. So the part left to people like me and or Tim, and Tim I think has got some examples for us, is finding scenarios where we could potentially even use the math that you just described, right? Because you don't walk outside and see a bunch of triangles out there for you to measure. You have to come up with.
And if you do, there's help for you.
So Tim, give us some examples.
Okay, so I'll give one example. This kind of math can be used to, and I know this is true because I just looked it up, to calculate the distance of nearby stars, for example. So, and generally, I think it can be used for calculating orbits, planetary motion, or anyways. There's one for you. Astronomy.
But do you want to go into how it's used to do that?
I'm confused. How do you measure nearby stars?
Okay, well, Matt, do you want to take this?
All right. So the way that you would use trigonometry to find the distance to a nearby star, if you're sitting there on Earth, you can take an angular measurement from your point on the ground to that star off in space, and that's cool. But that will give you one angle in a 3-point triangle. Now the problem is, in order to have a triangle that you can solve, well, you need more than a single angle. And so what you do is you wait 6 months, and you wait until the Earth has zipped around to the other side of the sun, and it's now at a different point in space. Do I know how far the Earth has moved? Well, yeah, yes. I do. I know the distance of Earth's orbit. I've figured that out. So essentially, I now have another point in my triangle. My first point was Earth back in spring. My second point is Earth in the fall, and my third point in my galactic triangle is that star that I'm measuring, or measuring the distance to. So now that it's fall, I take that same angular measurement, and I have another angle. And what I have now is I have the length of one side, that is the distance between Earth in the spring and Earth in the fall. And I have the two angles that are connected to that side, the angles to that star. Because I have those two angles, and because I have the length of the side between them, I can now use trigonometry to solve for any of the other sides, which will give me the distance to that star. And I can use, the easiest thing to do would be to use the law of sines. Because if I have two of my angles, do I have my third angle? Yeah, I totally do, because it adds to 180. So I have the angle at the star that is the angle between my two Earth points, if that makes any sense. So by measuring the angles from Earth to the star in the spring and from Earth to the star in the fall, I can solve for the angle at the star between those two Earth points. Now then, I can use the law of cosines because I know the angle at the star. I'm sorry, not the law of cosines, the law of sines. I know the angle at the star. I know its opposite side. That's a function of Earth's orbit. I know how far the Earth moved I know the straight line distance that it moved between spring and fall. So essentially, if the star is at point C, angle C, then side C is the straight line that you would draw between where the Earth was in the spring and where the Earth is now in the fall. If I have angle C and I have side C, then I can use the law of sines because I know that C over sine C is equal to A over sine A. And A is going to be my distance between Earth in the spring and the star. And I know what sine A is because I figured out that angle when I measured back in the springtime. And I can very quickly algebraically solve that problem and get the distance between Earth and that star in both spring and fall. So that is, if you're interested in figuring out how far away some star is, measure its angle from the Earth in the spring, and then 6 months later in the fall, do some trigonometry, use the law of sines, and you can figure it out.
Okay.
Now,
So
I presume you would have to have some pretty refined measuring tools to calculate those angles, right? I'm betting that it's a very small angle. Like you would have to be pretty precise to be able to calculate it. Am I right?
Yeah. Well, and you'd also want to align your angular measurements on Earth correctly. They have to be. Boy, this is going to be exceptionally difficult to explain. But when you take your angular measurement to that star, you need to be measuring the angle between where the star is now and where the Earth will be 6 months from now. That's the angle that you're looking for. And if you do that at both points, then you will get the correct angles. You can then solve for the third angle at the star, and then use the law of sines and some basic algebra to solve for the distance.
okay,
Yes,
so
having a sensitive and precise instrument really helps.
does matter, exactly. So for the layman, given the podcast title, what I was doing during some of the time that Matt was explaining the trigonometric functions. Is that the word?
Yes.
Anyway.
Trigonometric.
Yes,
Yeah,
those.
All right.
Trigonometric is when sheep herders and goat, shepherds use it on the steppes.
Okay. Okay, but so the layman is out there. He wants to know how tall a particular building is, or something along those lines, and he doesn't have a compass. He doesn't have any of this equipment he needs to in order to figure it out. So can he ballpark it in any meaningful way, right? If I'm at the, let's say the Eiffel Tower, can I figure out without looking it up? Sure, I could Google it, but that's boring. Can I figure out how tall the Eiffel Tower is without any of these other tools? And so I was trying to figure out what the quick ballpark way would be to do it. So depending on whether or not which measurement system you use, metric or do we call ours standard? It can't really be standard, right? Is it English? Whatever.
Well, the units.
The units don't matter, but
no,
they
don't
matter in how I'm going to explain this for a layman. So let's say
Okay.
you then march off 100 feet, right? So, you know,
And for our international audience, feet is American for meters.
yes, is related to meters. So 30 meters, let's say. And, just by striding it out, every stride's 3 feet or essentially 1 meter. And so you get
I
that.
should
And
be
then,
very careful when I'm making deadpan jokes because I don't know if people catch that.
right.
No, feet and meters
I'll
are not
just
the
have a
same. I'm
little
sorry.
humor advisory. I'll be like, humor advisory, that was a joke.
Yeah.
Anyway,
Sorry, Carl. Go ahead.
yes. So now I'm looking back at the Eiffel Tower and I think to myself, well, I know one side of this triangle because I started obviously right underneath the Eiffel Tower. And now I ask myself, how do I get this angle? And I think to myself, I cannot, because I do not have a compass. So then you wonder, okay, well, what can I do instead of having a compass? Well, now what you can do is you can make yourself a little slope. So you get your buddy who's exactly 6 feet tall, or pretty close. For example, me. I'm close-ish. Once again, we're ballparking because we're laymen. So I'm 6 feet-ish. And now I take 2 more steps. So now I've gotten, 32 meters or whatever away from the Eiffel Tower, but I've got 2 meters along one side, and I know that I'm about, 1.8 meters tall or whatever it is. And so now I can figure out what my slope is. And if I can get my slope, I can take the inverse tangent of the slope. So, and once again, how does a layman get the inverse tangent of something? Well, you could bring up the calculator on your phone, but once again, we don't want to do that. So what we want to do is kind of get you want to get close to a number that's going to be 0.6, because it turns out if you get a 0.6 degree relationship, so if I'm 6 feet tall, go 10 feet out, so that's 3 meters instead. Instead of 2 meters, go 3 meters. And now I can say I've got about a 30-degree angle from the ground to the top of that guy that's 2 meters. That's not 2 meters. 2 meters is well over 6 feet, but 6 feet tall, right?
Well, and again, the reason you select 0.6 is because the tangent of 30 degrees, or I'm sorry, the cotangent, I guess.
Yeah.
Is that right? Is 0.6.
Right. So yeah, so now I've got that slope, and from that slope I take the inverse tangent, and now all of a sudden I know that and once again, I'm out there, I don't even need to know this. What I need to know is if I can mark 10 feet off, and this guy's 6 feet, and from the top, I can hit the top of his head up with on line with the top of the Eiffel Tower. I now know I've got about a 30-degree angle from the ground to the top of the Eiffel Tower based on that guy's head. And now all of a sudden I've got what I need to know in order to figure out how tall the Eiffel Tower is. I've got, 32 meters-ish away from the Eiffel Tower. I've got a 30-degree angle, and now voila, I use the, what is that, Law of Sines? Is that one? Adjacent side and the angle.
Yeah, you have the 2 angles, and you have the
adjacent
side between them.
Right.
So you would use the law of cosines.
So then you use the law of cosines, and now you've got the height of the Eiffel Tower, and all you need to know is how to solve for the law of cosines out there without your phone. Which
well, important to note that 32 meter distance you gave, that will vary depending on, well, many things, time of day, and I mean, that was just a notional number, right?
That was just random. I mean,
okay, actually, it won't vary based on time of day, but yeah, it was some measurement, however far it is.
Right, exactly.
You can measure out
so you can line up
to the point where you get that 30-degree-ish angle.
Exactly. If you can get that 30-degree-ish angle with that guy's head and the top of the Eiffel Tower, all of a sudden, if you've been measuring to that point, and you can say however many meters that is, and now you can say, okay, I've got the side, I've got the angle, and problem solved. Or it is very easily solvable at that point. So, and that's what that. So you no longer need a compass. You don't need all those other things. You can literally just step it off, get the slope for the angle, and now as a layman you can ballpark height of different objects out there and look like you are a genius. So, any last examples, Matt or Tim?
I think we've basically covered everything that any person could ever need to know about triangles ever.
Yes. And come back next time for when we talk about all the pyramid things that you need to know. Okay. Anyway, well, we're going to wrap this up, and hopefully you learned a little bit about the trigonometry here, and we'll come back with for our next episode. And until then, stay safe.